All right, so here we are. This is going to be our first jump into chapter number 18. Chapter number 18 is all about thermodynamics and kinetics. So there's a bit of math, but there's also some really important conceptual components to this chapter. But at any rate, we're going to go ahead and just jump in. So here's our learning goals for chapter number 18. And I did say 18, which means we have chapters 18 and 19, and that is the end of the content for the semester. For this chapter, we have to is it showing up? To functioning. Okay, that's going right now. So we've got a lot going on with this chapter. We got to know some laws of thermodynamics, entropy, entropy of a system, entropy of the surroundings, and then we're going to get into this rascal right here, Gibbs free energy. And then we're going to be comparing delta H enthalpy, delta S entropy, and delta G, which is Gibbs free energy. But with that said, this is chapter number 18, chemical thermodynamics. Now in chapter number 18, what we're going to be looking at is this graph right here. We've talked about this one before. This is a free energy diagram where we have the reactants, the products of a reaction. Then we have this intermediate right here, or this transition state. Energy is on the y-axis, and then our x-axis is basically the progression of our reaction. So in thermodynamics, or the study of thermodynamics, what we're interested in is the direction of the spontaneous reaction. We're interested in the initial and final states of our reactants and products. Kinetics, we are interested in, the speed or the rate of the reaction, the pathway between the initial and the final states. And those are the big components that we're interested in anytime we talk about kinetics or thermodynamics. So this kind of central transition area is what we're really kind of most interested in after it's all said and done. So you can basically look at central region as the kinetics, the speed of the reaction, pathway, whereas these green kind of flanking areas are thermodynamics, basically the state of our reactants and our products, as well as the direction of our spontaneous reaction in towards the products or towards the reactants. Now, spontaneous reactions, the term spontaneous is an important one that you need to be familiar with. A spontaneous reaction will occur without outside intervention. So on the left-hand side, we've got these ice cubes, and on the right-hand side, we have a glass that looks the same, filled with water. Now, this is spontaneous at a temperature above 0 degrees Celsius. Now, if I said that this was at 2 degrees Celsius, the reaction is going to be different. It's not going to be a spontaneous reaction. So if it's below 0 degrees Celsius, the reaction is going to be different. Now, the reaction will be spontaneous, T less than 0 degrees Celsius when we're going from the liquid to the solid. So that water is going to freeze spontaneously at a temperature below 0 degrees Celsius. Okay, so that's our first investigation into spontaneity of a reaction. Now, another important component or variable that we're going to be looking at is S, which is entropy. S, or entropy, is a measure of disorder or randomness in a system, in the universe, any number of things. Now, if we're to compare this to this right here, well, the two of them, which one of these is more kind of random? Well, if we look at the one on the right-hand side, we've got water molecules. These are our water molecules. Then we have these different atoms or ions kind of peppered about. So what's the order that we see of our water molecules? It's not really any order. Um, there's some water molecules that are right next to other water molecules. There's some water molecules that are right next to our purple ions or our green ions. Now, if we look at this system over here, do we have any sort of order? Absolutely. This cube in the center, those purple and green ions are packed really well together. They're organized. Now, if we compare these two, which one of them is more ordered? Well, that's pretty clear to see. It's this over here is more ordered. So that means that this on the right-hand side is our more disordered. In which case, if we're looking at A versus B, if we're to transition from A to B, disorder has increased. Entropy has increased. Now, if we're to go from B to A, by contrast, then our order has increased, therefore our entropy of our system has decreased. So the more ordered it became, the more that our entropy decreased. So on the left-hand side, we've got our lower entropy, and on the right-hand side, we've got our higher entropy system. Now, when we talk about entropy and other thermodynamic and kinetic properties, we also talk about spontaneity. So an increase in the entropy of the universe is the driving force for a spontaneous process. Okay, so an increase in the entropy, so something that leads to more disorder, is the driving force for a spontaneous process. So basically, any process that leads to more disorder, or another way to put it, that leads to less order, oh boy, is going to lead to, um, less order means more, or an increase in entropy. Now, delta S of the universe greater than zero for a spontaneous process. This is our second law of thermodynamics. We'll get to specifics in just a moment. Now, so here's our first question. A certain process has a delta S of the universe greater than zero. So that's a positive entropy change. So that means entropy has increased. Therefore, the amount of order in the system has decreased. So I always like to write this out. Say entropy, which is denoted by delta S, that has gone up. Therefore, disorder has gone up. Therefore, order has gone down. Now, this is delta S universe at 25 degrees Celsius. What does one know about this process? Option A is exothermic. Option B is endothermic. Option C, it will move rapidly toward equilibrium. Or option D, it's spontaneous at 25 degrees Celsius. Okay, so we're provided with this delta S universe is greater than zero. That indicates that the total entropy change for the process is positive. This implies that the system and its surroundings together experience an increase in entropy during the process. And so based on this, we can surmise that our reaction is B, endothermic. So when we consider some of these options, or the different answer options that are provided, we've got A, it's an exothermic process. Okay, so if the entropy is positive, if our entropy change is positive, well, that doesn't necessarily tell us anything directly about whether or not it's an exothermic process. So what we can say is that it's unlikely to be A, as opposed to B. Well, when our delta S is positive, that indicates that we have a system that's absorbing heat from its surroundings. So it's more likely that it's B than it's A. Now, with respect to option C, that it will move rapidly toward equilibrium, well, that doesn't really, uh, we can't really say that because the change in entropy doesn't directly relate to um, movement towards or away from equilibrium. Now, um, it's spontaneous at 25 degrees Celsius. That statement is more than likely going to be true, um, because delta S of the universe indicates that the process is spontaneous under the given conditions. So when delta S is positive, then chances are it is going to be spontaneous at 25 degrees Celsius. Okay. Now, next question or follow-up question. Does the 25 degrees Celsius in the previous question matter? So we're told explicitly in the previous question, sorry, that our delta S in the universe is greater than 0 at 25 degrees Celsius. Um, so at 25 degrees Celsius, does that temperature matter? Option A, yes, because the thermodynamics require temperature be specified in every problem. B, no, because temperature does not affect spontaneity. C, yes, because spontaneity can change at different temperatures. Or D, no, because once you know the spontaneity of the reaction, it is true at all temperatures. So our best answer for this is really going to be C, because of the fact that with answer option C, um, we're we're basically told that we're provided with a specific temperature, and then we're presented with, well, what if the temperature changes? So C is our best answer there. The spontaneity can change at different temperatures. All right. Now, what are the factors that contribute to entropy? It contribute to a system is order increasing or decreasing? Well, first and foremost, or first of all, what we've got are phases. So now different phases of matter exist, including gases, liquid, solid, and crystals. Um, what we have here is a measure of different, or kind of a ranking of different uh, different substances and their rankings from their levels of order. So if we've got gas, liquid, solid, and a perfect crystal, I always think about these in terms of like, let's imagine that we have atoms that make up these different uh, phases. So in a perfect crystal, so a solid, you've got, let's go ahead and say three atoms. Those three atoms are never going to move, or they're basically not going to move away from one another. Now, if we compare that to a solid, well, we've got a little bit of a different, it's a little bit less ordered than a perfect crystal. A liquid, think about the atoms that make up a liquid. They're going to be moving all over the place. And a gas, they're moving even more so. So we have phases in terms of their um, greatest entropy. Right here to our lowest entropy. Now, higher temperature versus lower temperature. Generally, at higher temperatures, particles have more kinetic energy, leading to an increased disorder and typically favoring a gaseous state as opposed to a liquid or a solid. Changes in moles of gas, well, if you change the number of moles of a gas, that can significantly impact the entropy change of a reaction or a process. The more amounts of a gas, essentially, the greater amount of that disordered something that has been added. Then overall amounts, Well, extensive properties are dependent on the size or extent of the system and are additive for separate systems. So we have our entropy increase from our crystalline solid to a liquid to a gas. Now, this graph right here shows us our phase changes going from a solid to a liquid to a gas. And what is increasing? Well, enthalpy and entropy are both increasing as we go from a solid to a liquid to a gas. As we go from a gas to a liquid to a solid, what is decreasing? Well, both enthalpy and entropy are both decreasing. Okay, so for each of the following, select the system which has the greater entropy. Okay, so as we begin to look at this, there's some fundamentals to keep in mind. A system that has or an example of a system that has greater entropy is a system that has a gas versus a liquid. So a gas is more or has greater entropy than a liquid. A liquid has greater entropy than a solid. So let's look at a couple of these examples. We've got 1 mole of H2 gas versus 2 moles of H2 gas. What's the difference between these two? Just the abundance or the amount. Now, if you remember from one of our previous slides, we talked about was overall amounts. So when we have more of a substance, well, then that's going to lead to an increase in entropy. So between these two, 2 moles of H2 has greater entropy than 1 mole of H2. Now, H2O as a solid versus H2O as a liquid, which is going to have greater entropy? Well, that liquid is going to be more disordered than, say, that solid. I2 gas versus I2 solid. Well, both of these, the substance, it's I2 in both cases, but the gas is more disordered or less ordered than that solid. 1 mole of O2 gas versus 1 mole of O3 gas. Okay, this is kind of tricky because what do we have here? We got O2 and O3. Now, I think that one way to think about this one, so I think that it's helpful to compare these two substances, compare the O2 and the O3, and maybe even draw them out. If you remember the structure of O2, it looks a little bit like this. Each oxygen has 2 lone pairs of electrons. That gives each oxygen a grand total of 8 electrons around. Okay, so this is 2 atoms of O2. It's a pretty good structure of what it looks like. Now O3 has this kind of structure like this. If I remember correctly, it's actually going to be, well, here's one structure of it. There, boom, but then there's also right here. You have that. This is effectively 2 different models, 2 different structures. And ultimately, there's a word that we've talked about a little bit in this class, but it definitely came up in Gen Chem 1, and it's definitely going to be a big part of your organic chemistry classes, is that these 2 structures are resonance structures. They're resonance stabilized. Okay. So essentially what this has, let's think about this as a, comparison. O2 is one possible way that those 2 oxygen atoms can be arranged in space. Okay. Now, O3, by comparison, that's 2 possible ways that O3 can be coordinated in 3D space. So effectively, you can make a strong case that O3 is more complex than O2. And by it being more complex, well, it has a higher degree of entropy. So between these two, O3 and O2, O3 is going to have the greater entropy. Now, next up is the sign of delta S. Predict the sign of delta S for each of the following changes. Delta S of greater than 0 indicates an increased entropy. So we have AgCl as a solid going to Ag plus and Cl minus. So that's silver chloride going to a silver ion and a chloride. So that's one solid going to two aqueous ions. So this dissolution, or this dissociation, is taking one contained thing, breaking off into two different things. One thing becomes two things, one ordered things becomes two kind of random things. That's definitely going to be a delta S that is greater than 0, more disordered. That's a positive delta S. Next up is 2 moles of H2 react with 1 mole of O2 to produce 2 moles of H2O. Okay, for this one, what we can do is a couple of different things. We take a gas, another gas, and we make a liquid. Okay, so my first question is, if you take a gas where the atoms are kind of all over the place, and then you take that gas and you condense it down to a liquid, well, is there more order in the atoms and molecules that make up that liquid? Absolutely. So on one hand, G to L greater, sorry, greater ordering. So negative delta S. Okay, so that's one component to think about. In addition to that, we have 2 moles of the gas plus 1 mole of the gas that make 2 moles of liquid. Okay, so we're going from 3 things down to 2 things. That is also going to be contributing to a negative delta S. That system became more ordered. Now our last one, let's see how complicated this is. 2 moles of H2S plus 1 mole of SO2 is going to produce 2 moles of H2O gas and 3 moles of delta S, or sorry, 3 moles of sulfur. Okay, so let's think about this. I'm going to look at this as 1 and then, or sorry, 2 and then 1. We got 3 moles of a gas going to 3 moles of a solid and 2 moles of a gas. So 3 gas to arguably 2 gas. Well, also you got 3 gas to a solid. So our starting point was definitely a disordered system. Now that last one is a little bit challenging. So we have gaseous hydrogen and oxygen that combine to form that liquid water, and that sorry, and that, or that this one, like I was saying, is fairly complicated. We've got this gas going to, well, 3 moles of gas going to 2 moles of gas. We've also got this gas forming a solid. So both of those things kind of suggest that our system is becoming more ordered. But one of the tricky parts about this is that it's gaseous water. And the formation of that gaseous water can lead to an increase in entropy due to the increased molecular motion and disorder. So this question, this last one, it's really kind of tough, and you can justify it as delta S is negative, but chances are this is going to be delta S. It's positive, just as this one is. Or sorry, this one by comparison, um, our delta S, chances are it's going to be a negative value. There. Now, which of the following can a decrease results in a decrease in the entropy of the system? Okay, so we're going to look at all of these different answer options. Excuse me. We've got O2 going to O2 gas at 300 degrees Kelvin or 300 Kelvin going to O2 at 400 Kelvin. Now, this process is probably not going to result in a decrease in entropy because what we're seeing is the temperature goes up and that gas is only going to become more disordered. And number two, we've got N2 at 25 degrees Celsius as a gas going to an aqueous substance. That chances are, well, we're going from a gas where there's some order to an aqueous substance, which it's something that has lost an electron. So it's even more, or it's even more disordered. So that's not going to result in a decrease in entropy either. Now, answer option C, solid water going to a liquid at 0 degrees Celsius. Okay, so this process is basically our solid ice melting. Now, that transition from a solid to a liquid typically results in an increase in entropy due to increased molecular motion and disorder. And so that becomes more chaotic, and so that's not going to decrease in entropy. Answer option D is NH3 ammonia at negative 34.5 degrees Celsius all the way to a gas at negative 34.5 degrees Celsius. Well, all that we're seeing is a liquid going to a gas, and a liquid going to a gas is a phase change that's going to increase our entropy. Now, answer option E, 2 moles of H2O go to 2 moles of H2 and O2. So we're taking 2 moles of a gas and going into 3 moles of 2 other gases. So this is our water decomposing into hydrogen gas and oxygen gas. This is probably going to result in a decrease in entropy. So this particular one will more likely be our correct answer, because what we've got there is water going to these 2 particularly small, well, 3 particularly small substances. Now, calculating entropy of a phase change. Delta S of the phase change is equal to the heat of the reverse reaction divided by temperature, which is the same as delta H over T. Now, our T is our temperature in Kelvin, and our units of S are joules per Kelvin, and our scale for Q is the amount of the substance. So the heat of vaporization of ethanol at 25 degrees Celsius is 42.3 kilojoules. What is the entropy change of 10 grams of ethanol vaporized at this temperature if the molar mass of ethanol is 36.07 grams? So to solve this sort of problem, what we need to do is we need to convert our mass of ethanol to moles. So that's the first thing that I'm going to do. And is it 10 grams? Ethanol, you can also write as ETOH. And that has a molar mass of 46.07 grams. That's going to equal to 0.217. Okay, so we've got 0.217 moles. The next thing that we need to do is we need to calculate Q, which is going to be our heat evolved. Q is equal to this 42.3 kilojoules per mole times our number of moles. So 42.3 times 0.217. And that is going to equal 9.817 kilojoules. And that's it. It's not kilojoules per mole. So now what we need to do is we need to convert our temperature from 25 degrees Celsius to Kelvin. 25 plus 273.15 equals 298.15 Kelvin. So now that we have that, we can calculate our delta S by taking this Q divided by our temperature, 298. Let me root the T. So essentially what we're doing, that right there. So this is 9.817 divided by 298.15. And that's going to get us to 0.038 kilojoules Kelvin. So that's going to be 0.0308 kilojoules per Kelvin. There we go. So what this tells us is that the entropy change when 10 grams of ethanol vaporizes 25 degrees Celsius, or at 25 degrees Celsius, that entropy change is this 0.0308 kilojoules, which is the same as 30.8 joules per Kelvin. All right, so I think so. This equation right here, S, which we've used for entropy, is equal to K times the natural log of W. Okay, so S is our measure of entropy, and this is what we're going to use to quantify it. K is a constant. That is this 1.38 times 10 to the negative 23rd joules per Kelvin. This is equal to R divided by Avogadro's number. So our gas constant divided by 6.02 times 10 to the 23rd. Okay, so check. Natural log of W. Okay, well, W is the number of energetically equivalent arrangements called microstates. W is equal to x to the n power. Okay, x is the number of locations and n is the number of particles. Okay, so essentially what this boils down to is W. So W is the number of energetically equivalent arrangements called microstates. W is equal to x to the n. X is the number of locations and n is the number of particles. So here what we've got is all of these different kind of dominoes. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's our 8 different dominoes, which are divided up into 2 different spots, basically. We could argue that that would be 2 different locations for each one of those dominoes. So that gives us 16 for x. Now, n is the number of particles. Here we have a grand total of 1, 2, 3 particles. So we have 16 to the 3rd power. Would be that sort of calculation if we were to quantify it. And this is just the model. Now the entire, like the point of the Boltzmann constant, and sorry, the Boltzmann equation is to relate a macroscopic change to a microscopic behavior or an atomic or molecular behavior. So when we look at this, let's predict the sign of delta S for the following change between microstates. Here what we have is two different things in two different locations. And then those two different things are brought together into one location. So if we think about this purely from the standpoint of order, well, 1 and 2, number 1 is less ordered than number 2, in which case we have a delta S that has become negative. So our laws of thermodynamics. The first law of thermodynamics states energy can neither be created nor destroyed. The energy of the universe is constant. Our second law of thermodynamics states that in any spontaneous process, there is always an increase in the entropy of the universe. The entropy of the universe is increasing. So this is what we've kind of been dancing around for a little bit. Then the third law of thermodynamics is that the entropy of a pure crystalline substance at absolute zero is zero. That thing cannot change. The second law of thermodynamics, any overall change of the universe is equal to a change in the system combined with the change of the surroundings. The system is the part that we're interested in. The surroundings are everything else. So for spontaneous reactions, our delta S of the universe is greater than zero. How can we detect or how can we calculate delta S of the universe? We can use the Gibbs free energy equation. Now, by definition, this is an equation that you'll use not only in this class, but when you go on to physical chemistry and biochemistry, you'll use this equation. So delta G is equal to delta H minus T delta S. Okay, delta G, or G, is called the Gibbs free energy. A process will be spontaneous at constant temperature and pressure only if delta G of the system is less than zero. So a negative delta G indicates something is spontaneous. So being able to predict if a process is spontaneous or not is important. Now, delta G of the system less than zero is equivalent to saying delta S of the universe is greater than zero. Okay, so think about these two things and kind of, keep that at the forefront of your mind. So a portion of energy change of a reaction available to do useful work. Okay, spontaneity changes when delta G equals zero. Find the temperature when delta G equals zero. Spontaneity is different above and below this temperature. Okay, so what we want to do is set delta G equal to zero. That is going to be equal to, or that's going to set 0 equals delta H minus T delta S. Then you can rearrange this, adding delta or T delta S to each side, giving a T delta S equals delta H. Then divide each side by delta S, and you get T is equal to delta H over delta S. So the delta G is zero. So no Gibbs free energy change when T equals delta H over delta S. Now with that, you can predict whether something is spontaneous or not based on the following table. So when delta G is less than zero, that is a reaction that is going to be spontaneous at all temperatures. Now, so what you're going to be looking for there is delta H that is less than zero and delta S that is greater than zero. What I think is really helpful to look at these and kind of piece these together is say, all right, A reaction is going to be spontaneous when you've got negative delta H and a positive delta S. When delta H, enthalpy, and entropy are both negative, well, that's going to be a spontaneous reaction, but only at low temperatures. When delta H is positive and delta S is positive, then that's going to be spontaneous only at high temperatures. When delta H is positive and delta S is negative, that's going to be non-spontaneous for all temperatures. Okay, so that gets us through some of the important parts and some of the tougher parts about chapter number 18. I'm going to go ahead and stop the recording. But before I do, this is stuff that we're going to work through. We're going to work through some practice problems on Thursday in class. If you have any questions about this, bring those to class on Thursday, and hopefully we'll address them through our practice problems. All right, well, have a good one.